Welcome back. We're into podcast 2, and the good news is I'm going to review with you again. Constantly, we are revisiting other concepts to build up your confidence in them and to really hopefully make it to a point where you feel comfortable with what we're doing and are able to apply it into new situations. So, today's review topic is calculating amounts. And amount, if you remember back, is in chemistry always referring to number of moles. So it's a very specific amount of a specific something. The reason why we're reviewing this is we're getting into this week and next week one of the all-encompassing, super important concepts of chemistry, which is called stoichiometry. Not stoichiometry, but stoichiometry. Okay? So important that you recognize the different formulas that we've used in the past to calculate amounts, which are going to be then utilized within a balanced chemical equation, are really important. In other words, guys, I have quite a typo here. Relative amounts. Sorry about that. That's supposed to be relative amounts. Anyway, okay. So represent the relative amounts of the chemicals that react. Now, guys, familiar equations. Check out these, right? Now, for each of these, I'll highlight yellow for you. N is the amount, number of moles. N is the amount, number of moles. N is the amount, number of moles. The first formula is one that was introduced to you in Science 10. But the N equals CV is a new one from this year, where C represents concentration. That's one that you hadn't done in grade 10 science. And the last one is also new from Chemistry 20, and this is dealing with our gas laws, right? So, ideal gas law, PV equals nRT. It's just been rearranged so that N is by itself. Take note that we've got volume present in our concentration one, right? There it is, volume. And we've got volume, of course, present again here, but I want you to think way back in your brains. This one also involves pressure. And it also involves, going back in your brains, temperature, right? Now I'm going to remind you with a couple of these since it's been a little while, that concentration with this formula, this one hasn't been quite as long as a molar concentration, which means it's always in moles per liter for units. That means the volume has to be in liters as well. Otherwise our units won't cancel out to leave us with moles. Within the context of the ideal gas law, it's been a while, but pressure must be in the units of kilopascals. Volume must be in the units of liters. R is representative, if I've got room to write it here, that unit, can you read that? Universal gas constant, right? So that universal gas constant, if you think back, is 8.314, and the units are gigantic. Kilopascals times liters over moles per Kelvin. And the hint that I gave you when we were in the gas laws unit, which is unit B, is by seeing those units, you know that you're going to have pressure in kilopascals. You know that volume is going to be in liters. You know that you're going to have temperature in Kelvin. And that's because they're written there right into the context of the universal gas constant. Speaking of which, temperature, Kelvin, right? At 273.15 to any degree Celsius value, and it will now be in Kelvin. See, told you it's important to review this stuff. It's been a while. Okay, let's put it into the context of some questions. Example 1, calculate the amount. Remember what I said, amount references number of moles. That's an N. What is it an amount of? Potassium carbonate. That's key, an ionic compound with potassium ion and carbonate CO3 2 negative anion. A 33.5 gram sample. Grams, guys, you've been given a mass. So the whole goal of this question is we're looking for N. N is equal to what? How do we go about this? Well, we've been given a mass of 33.5 grams. We need the molar mass, of course. I always, after the big M, if you remember this, I write my formula. So looking at the charges, positive 1, negative 2, drop and swap, we're going to need 2 potassiums and 1 carbonate. So molar mass of K2CO3 is going to be equal to, add them up, 2 potassium ions plus the molar mass of 1 carbon ion plus 3 times the molar mass of of oxygen. There we go. 138.21 grams per mole. Alrighty, we have everything we need. N is equal to the number of moles, right? The amount, mass over molar mass. Some of you are still lazy when it comes to units. Every single time I will take marks off. Quit being lazy. Put the units in. Are there exceptions? No. Put the units in all the time. All right. 33.5 grams is what we started with. That's going to dictate our sig digs. So we're going to have 3 significant digits, which gives us an amount of 0.242 moles. There it is. Review should feel familiar to you. Okay, let's try another example. What if we are trying to figure out the amount, ding, 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 amount, you see that language, guys, that's N, of zinc nitrate. Important to know what we're dealing with, a zinc 2 plus ion in an ionic compound with NO3 negative. It is dissolved to prepare 750 milliliters. Think about this. Milliliters is a volume measurement, so that's going to have something to do with V. And we're also told that we have a concentration of 15.8, take note, millimoles per liter. Well, guys, this is not quite in the right units yet, but it's a concentration. How do I know that? Because I memorize. Concentration is in moles per liter. Memorizing which units go with which variables is super useful. Okay, check it out. Let's write down what we know. We have a volume of 750 milliliters. Volume for concentration needs to be in liters. So divide it by 1,000. This is 0.750 liters. We have a concentration of 15.8 millimoles per liter. Not a typo, milli. How do you deal with that? Well, that little M is a prefix. Go to your formula sheet again, guys. If you look right here, you have that, and you know that milli is representative of 10 to the negative 3. So you can substitute that right in. That means the concentration is 15.8. I'm going to substitute in for that little m with times 10 to the negative 3. Now I just continue on with moles per liter. There we have it. We now have our correct units. We have volume with liters. We have concentration of moles per liter. Honestly, does this question ask for mass? No, so I don't even have to deal with my N equals mass over molar mass. This question, I've got everything I need to get the amount. N equals C times V. And yeah, I've got the volume. I've got the concentration. We're good to go. Concentration is 15.8 times 10 to the negative 3 moles per liter. Volume is 0.750 liters. Look at how those units cancel out. Liters on the bottom, liters on the top. We will get moles as our answer, which is exactly what we want. 3 sig digs is dictated by what's in the question. 1.19 times 10 to the negative 2 moles. I hope, guys, when you're going through these podcasts and listening to them, that you're pausing and number crunching for yourself. That's the best way for you to learn this stuff, is don't just listen, do. Write the notes as I'm talking to you. Double check with the posted PDF of the completed notes. Did you miss anything? Did you catch everything I said? I mean, as interactive as you can make this for yourselves, in a less than ideal circumstance, you will reap the benefits, truly. Let's do one more example that goes back into that ideal gas law. How do I know that this is ideal gas law? There's a few hints. Number one, I'm dealing with a gas, helium. That's a big hint. Number two is volume is being listed, but you might still be going, maybe this is a solution. Well, if you needed more of a hint, hey, pressure, guys. And then even past that, you're given a temp. You bet this is our ideal gas law, for sure. So write down what you know. Been given a volume, 8.00 liters. Been given a pressure. It is in the correct units, 103 kilopascals. Our temperature is 22.0 degrees Celsius. And again, it's been a while. You deal with this to make it Kelvin by adding 273.15. Once that's added, we're at 295.15 Kelvin, right? Don't lose sight of doing that. R is the universal gas constant. It's on your data sheet. You do not have to memorize it. Kilopascals per liter times moles per Kelvin. Going back to your data sheet, guys, if you, go back over here and look, there's huge hints, right? This is your hint as to what to add, the 273.15. This is where the universal gas constant is, R. They're on your sheet. Just know where to find them. Alrighty, let's build this thing. We are looking for the amount, in other words, N. So I've rearranged PV equals nRT. We get N equal to PV over RT. Plug in what you know. With units, 103 kilopascals times 8.00 liters. All of that divided by 8.314 kilopascal times liter over mole times Kelvin multiplied by the temperature, 295.15 Kelvin. Here's where there's often a mistake. Don't forget to use your calculator properly. You want to take the entire top divided by the entire bottom. So if you put brackets around where appropriate, you will get to a more likely correct answer. Alrighty, N, the amount is going to need 3 sig digs, is dictated by the original values in the question. We have 0.336 moles. And there you have it, folks, a review of calculating an amount. Now, the questions in the assignment get a little more complicated than this because they might incorporate more than one formula into the same question, especially N equals mass over molar mass. You can use that in the context of any of them. So be prepared for multi-step questions. Alrighty, homework. You can now complete another 4 questions, and you're definitely 2/3 done the homework. Once you're done that, the last thing we're doing is that introduction to stoichiometry. We're looking at balanced reactions. Man, guys, this is key, what's coming up in the next podcast. And it is the building block for the entire rest of this year, this unit. And it is the building block for Chem 30 and Chemistry Beyond. So, yeah, pay attention, do your own work, quit copying off each other, figure it out for yourselves. Talk to you soon.